Hello, this video is entitled Divergence, or is also known the Gauss Theorem. So one book may call it Divergence Theorem, one book may call it Gauss Theorem, but it's the same thing. In this section we're going to relate surface integrals to triple integrals. And we'll do this with the Divergence Theorem. So this could be fun. Now they're bringing us back from 15.4, this from Green's theorem. So there's the Green's theorem formula. And F dot n can also be the divergence of F dA. So it's telling us the divergence theorem gives a relationship between a triple integral over a solid region and the surface area integral over the surface Q. All right, so let's take a look at this. And I'm sticking with oriented outward again. So here's the gist of the divergence theorem. The divergence theorem says we can essentially find a surface integral that was f dot n ds, which was the last way we did them in when it's vector field. We did that in the surface integral video. We did it as a vector field, and we dot it with n. That was one we had n was negative zx, negative zy, comma 1. That was the normal vector because we're going oriented upward. Well, anyway, forget that. We're going to do this now. I'm not saying forget it completely, but I'm saying just forget it for now. We're going to do this triple integral theorem called the divergence theorem. This says that you can just relate this to a triple integral by finding the divergence of f and integrating it across a volume region. It will give you the same answer as evaluating the surface integral. Let's try this out. And okay, that's one thing you're doing. You're finding the outward flux. If we're going outward, yeah, that's the flux is the term. In the last section, I also mentioned flux integral. Keep getting myself. Let me scroll back, bring the video up bring the notes up from the last section. Yeah, that's the flux integral right there, is the f dot n. So that's essentially what we're evaluating here. Well, this will be kind of easy from a limit integration standpoint. We're doing a cube, which I don't think I even did any cubes in that other section, actually, because that's the easiest thing you can have. Cube is like having a rectangle, meaning the values are fixed. So 3, 3, 3. You're going to have just 0 to 3, 0 to 3, 0 to 3. And here's our vector field, x squared, y squared, z. Let's see what we have. So remember, there's the divergence formula we saw in another lesson early in the beginning of this chapter. So there's the vector field rewritten in component form. Make it a little easier, I think, but not hard either way. So the mx, the partial of this one respect to x will be 2x. The partial of the middle one respect to y will be 2y. And then respect to z, the partial of the third term, because it goes m, n, p in that order. These variables didn't have to match up perfectly either. Keep that, because obviously you can have x's and y's and stuff all mixed up. So the divergence is 2x plus 2y plus 1. And we just integrate this from 0 to 3, 0 to 3, 0 to 3. All right, so let's just integrate this, and that will be our answer. So the first thing, I just chose dz, dy, dx. Really doesn't matter. They're all 0 to 3, so it really wouldn't make any difference what order. So I just left this alone for a second since there were no z's there, and just integrated dz and got z and left that sitting there. Put in 3, 0, and 3, you'll get a 3, which you can then bring to the outside. Now, though, since I have y's and stuff in there, I've got to integrate this with respect to y with each term. So 2xy, antiderivative of 2y would be y squared. Antiderivative of 1 would be y. And then we plug in 3 and 0 for y, and we will end up with 6x plus 12. Plug in 3 everywhere, so that's 9 plus 3 right there is 12, and that's 6x. 6x plus 12 with that same 3. Integrate now with respect to x. We have 3 times 3x squared plus 12x from 0 to 3, and we will get 189 as the answer. There we go. So like I said, I like to keep these problems pretty reasonable. You know, I guess obviously this could be challenging if the integral got out of hand, but that is not my intention. All right, this one's looks like fun. This x squared plus y squared business makes me think we're going to have polar here, but let's see. So there's my f, and I'll get the divergence of that first. So the derivative of 2xy squared with respect to x would be 2y squared. The derivative of the middle term, derivative of y, would be 1, so it's plus 2x squared. And then the derivative of this last term has no z's, so it'll just be 0. I just didn't show the 0. So we'll leave this alone for a minute. And, well, now let's go ahead and write it like this. So we're integrating 2y squared plus 2x squared dv across this region right here. Yeah, so everything's kind of set up. The region's polar. Now it gives you the values for z, 0 to 8, but then you'll get the y from the circular region inside that circle with radius 2. So it's a circle with radius 2 from z equals 0 to z equals 8. So we'll start with this in cylindrical. So this is cylindrical coordinates. I'm not sure if I said polar coordinates or not. Well, okay. Well, cylindrical is polar with a z, basically, so I wasn't far off, but yeah, it's going to be cylindrical. So z goes from 0 to 8, and then it's a circle with radius 2, so it's going to go 0 to 2, 0 to 2 pi. It just says less than or equal to 4. It doesn't say anything limiting, you know, what does is x positive or is y positive. So you would assume it's the entire circle, and it is. Obviously, if it would have said like y is greater than or equal to 0, it just would have been a half circle, and you would have gone 0 to pi instead of 2 pi. Well, now, this is convenient for polar also, because 2y squared plus 2x squared equals 2r squared. And, of course, you have the r that goes with there automatically, so now this is going to work out all right. Now, I combine these two terms together to get 2r cubed, and the first integral is just integrating dz. Integrating dz is just going to give me z. So I put in 8, put in 0. 8 minus 0 is 8, so I'll put the 8 here. 8 with the 2 makes 16. So I'll bring the 16 outside. Now we're up to the r, so I integrate r cubed, which would be 1/4 r to the 4th, 2 and 0. 2 to the 4th is 16, so 1/4 16 is 4. 4 minus 0 is 4, so you take the 4 times the 16. Now we just have d theta, which has an antiderivative, of course, of theta. So 4 times 16 is 64. D theta is theta. 0 to 2 pi, tosses the 2 pi in there. And we get a lovely answer of 128 pi. There it is. All right, not too bad. Okay, this one we're going to have to use spherical coordinates because we have our sphere region. I mean, this probably could be converted to cylindrical, but as we've seen in that section, spherical and cylindrical coordinate integration, boy, sometimes you take something that's supposed to be spherical and you convert it to cylindrical, it can't really be integrated. So that's no good. But this one's actually going to work out beautifully. Divergence, so the derivative of 5x cubed with respect to x will be 15x squared. 5y cubed with respect to y will be 15y squared. And 5z cubed with respect to z will be 15z squared. So 15 x squared plus 15y squared plus 15z squared is 15 rho squared. Because x squared plus y squared plus z squared equals rho squared. So we have 15 rho squared right here. That's the divergence. And the region is rho squared sine phi. Remember, that's the one that goes in there all the time. Rho squared sine phi, d rho, d phi, d theta. Now, because x squared plus y squared plus z squared is rho squared is going from 4 to 9, so you have to square root the 4 and the 9 to get the region for limits for rho. So square root would be 2 and 3. So that's why that's a 2 and a 3 here from those square roots. And then now, remember that the maximum for phi is 0 to pi. And then the outside 0 to 2 pi. We don't go 0 to 2 pi for the middle one. So that's the maximum there, 0 to pi, meaning we're including the entire sphere that way. So we got the first integral with respect to rho. So I have 15 rho to the 4th. So I brought the 15 out, left the sine phi there for the next integral. Rho to the 4th will be 1/5 rho to the 5th. Put in 3, put in 2. The 15 times the 1/5 will be 3. So 3 to the 5th minus 2 to the 5th ends up being 211. So I can multiply those together to get 633. Now we're ready to integrate sine of phi respect to phi. Antiderivative of that would be negative cosine. Put in pi, put in 0. Cosine of pi is -1, so the negative of that would make it +1. Cos of 0 is 1, makes that -1. So actually, it ends up being 1 not minus -1. I kind of wish I would have gotten rid of this negative and reversed those two, but I'll just sort of do that verbally without writing it. So suppose I reverse these, got rid of the negative. Cos of 0 is 1. Cos of pi is -1. So it would have been 1 minus a -1. So it does end up being 2. So I have it correct as 2, but that extra negative could make it a little confusing. So I have 633 times 2, 0 to 2 pi d theta, which just puts the 2 pi in there. So it ends up being 2532 pi. There it is. All right, we're doing an outstanding job. Okay, I found some information there I thought was maybe interesting to kind of look at this. Divergence measures how a vector field spreads out or diverges from a given point. So it's moving away. It gives it a positive result. So the figure on the left has positive divergence. You see everything's kind of moving away from the point, whatever point here it is. It's kind of all going up and away. The middle one essentially has 0 divergence since they're not really spreading out at all. They're just kind of going in a straight little line like that. Nothing. Oh, and like it's explained here, that because the vector field is constant, because they're all going in the same direction, that also indicates in the divergence the derivative would be 0 also for that reason. Now this one looks kind of like a gravitational sort of idea. You know, they're all kind of sucking inward. We would call that negative divergence because they do have a pattern. It's just an inward pattern, and they're not all the same. You see the vectors are all at different angles. They're heading sort of the same direction, but they're not identical vectors like this one picture over here. It's kind of doing the opposite of the first one, so you say it has negative divergence. So, all right, you're not going to be tested on that. So, but I thought that was kind of an interesting thing to add there. Let's try another example. All right. So, here's our vector field. Here's our region, wedge cut from the plane y plus z equals 4, and a cylinder. X equals 4 minus 9y squared. Well, let's get the divergence first here. Derivative of xy respect to x would be y. the derivative of y squared would be 2y, and the derivative of the last one with respect to z would be negative 2y. So those cancel and just leaves y. So we're definitely integrating y. Yeah, I think there's no reason to worry about converting this one to any kind of cylindrical or spherical. This will pretty much be rectangular. So now I think we kind of have a little bit of choice on the order here. It doesn't matter. So you can see on this one, I chose to start with this one first, but I could have started probably with this one first and went df. But I started with this one first so I could solve for z in terms of x and y, but it's only y. So you see I'm going from 0 to 4 minus y represents dz here. And of course this y is the divergence y right there. That means x, looking at this middle one, will go from 0 to 4 minus 9 squared. Then now, how do I get the limits of integration? So actually, I didn't go dz, dy, dx, excuse me. I went dz, dx, dy. I left that one last to be the constant. So, then how do I get the limits of integration for y? Well, I essentially just took this equation, and then, as you integrate outward, remember each variable kind of assumes it's a 0. So I can put 0 in for x and solve for that equation right there. And I'm going to get 9y squared equals 4. Y squared equals 4 over 9, so y equals plus and minus 2/3. But we're in the first quadrant. Probably should have said first octant there, not quadrant. But anyway, so that eliminates the negative. So we're going only from 0 to 2/3. Okie doke, so there's our integral. Let's evaluate it. And so the first one, respect to dz, we'll just toss a z in there. So it brings 4 minus y and 0. So it brings a 4 minus y in there for z, multiplied by y. So it makes it, now I went ahead and distributed here, 4y minus y squared. The next integral is with respect to x. So you can leave the 4y minus y squared alone. Integrate respect to dx with x, just be x. So, 0 to 4 minus y squared. 4 minus 9y squared, excuse me. I'm looking right at it, but I'm saying it wrong. So I put this in here, so I have 4y minus y squared times 4 minus 9 squared, minus 9y squared. So you have to FOIL this out. So it's just a little arithmetic here, but it's not a complicated integral. You FOIL this out and get these 4 terms right here. None of them are like terms, so you can't combine them together before you integrate. So you have to FOIL that out to get these 4 terms, and then just use basic integration rules to integrate them. So take the antiderivative. That one would be 16y, will be 8y squared. This would be 36y to the 4 over 4, which will be 9y to the 4. 4/3 y cubed. 9/5 y to the 5th. Plug in 2/3 everywhere for y. I didn't show that, but obviously you'd use a calculator to do this. Got 656 over 405, and looks like, just for fun, I put that original integral there in Maple to see if Maple agreed with it. Although I probably should have had an answer for this one, right? Or do I not? Yeah, there it is. 656 over 405. So, yeah, I guess I just didn't feel like trying the other ones in Maple. But we were matching all the answers, so it didn't matter. Well, that concludes this video on the divergence, aka Gauss theorem.